Welcome to Growing Worlds, the podcast where we explore the science of exoplanets through conversations with early career researchers on the front line of discovery. I'm Lorenzo.
And I'm Jenny. In each episode, we meet a guest who takes us behind the science of planets, stars, and the missions that help us understand them.
Today, we are talking about space telescopes and one of the most ambitious upcoming exoplanet missions, Ariel, the European Space Agency's dedicated mission to survey the atmosphere of hundreds of exoplanets. And I should probably say it right away, this will not be a completely impartial episode because I am personally very involved in the mission.
So I'm going to be playing like devil's advocate here, trying to bring you two down from the excitement. So to guide us through what Ariel is, why it matters, and how we prepare a space telescope to do precision atmospheric science, we're joined by Dr Andrea Bocchieri from Sapienza University of Rome. Andrea, welcome to Growing Worlds.
Hello, hi there. Hi, Jenny. Hi, Lorenzo. I'm happy to be here.
Andrea is a postdoctoral researcher at Sapienza University of Rome and serves as a telescope scientist for the Ariel mission. His work focuses on spectroscopic characterization of exoplanet atmospheres and on preparing the mission to extract precise signals from tiny variation in starlight. From correcting instrument systematics to optimize observation strategies, Andrea's role sits right at the interface between hardware, data, and science. And at the time of this recording, Andrea is about to take his next step into his journey in science, moving to the European Space Agency as a system engineer to support the Ariel mission directly. So this conversation also is taking place in a very exciting transition point for your career, Andrea. Congratulations.
Thanks a lot, Lorenzo. I'm excited to be here and looking forward to the next adventure.
I think we should begin with your first adventures, right? We always like to start at the beginning, which is your personal story, before we kind of get into all of the interesting things about Ariel. So, how did your journey with exoplanet science begin? How did you get interested in working with this data, building a telescope, or at least contributing to building a telescope? Where does it all start?
Starts really, really early. When I was a child. So one of the first dialogues I can remember is with a fellow boy at the Materna school. So early days, like 4 or 5 years old.
Kindergarten.
Kindergarten, exactly. And there the question was, and we were arguing about it, was what's the difference between the sky and the space?
At that young age, like that's
Yeah.
so young to be
That's
thinking
deep.
about things like that. Yeah.
And we were arguing about it, and it was really funny. And this is the first conversation I remember from my early childhood. I don't know who was right, who was wrong, but I guess we had really funny ideas at the time. Moving on, I had a course during the elementary school by an astronomer. He was a volunteer teacher, so it's something that was extracurricular, and he was very passionate to teach young students about astronomy. One of the things I remember doing within this course is to measure the circumference of the Earth using the method by Eratosthenes. Sticks throw shadows at two different angles with a different latitude, and then we combine the measurements taken in Rome with those taken at a different school in Italy, and we were able to measure the circumference of the Earth. And we participated in a competition, and among elementary schools. And I remember the first one was a German school, but they used lasers, so that
Oh, that's
kind of
cheating.
that's cheating.
Hey, yeah, that is cheating.
I
I'm
mean,
pretty
you
sure that they
cannot
didn't have access to lasers thousands of years ago.
you can't fight a laser with a stick. Come on.
Yeah.
Yeah, so then moving on, I went to study at the University La Sapienza, and I took the physics curriculum with astronomy and astrophysics flavor, which means basically 2 exams about astronomy and astrophysics. Then moving on to the master's degree in astronomy and astrophysics, and meeting Enzo Pascale, who will
My goodness. Enzo, We have a connection as well because I too have worked with the man, the myth, the legend that is Enzo. So I did a project with him after I finished my masters and like the first part of my PhD. I did exoplanets with Enzo. Look at that! Look, we're all connected. Look at this,
Yeah,
beautiful.
we all met through Enzo here.
This is it. He's like the root cause of all of this. It's
We should
amazing.
invite him to the podcast eventually. I mean,
Yeah, like a special guest. We just keep name dropping him. Maybe we should. We'll have like a special feature episode, Christmas episode or something. Meet Enzo.
So basically, when upon meeting Enzo and finding out about exoplanets and the Ariel mission at the right time, because Ariel was then relatively young, was not adopted yet by ESA, um, and deciding then to pursue a thesis, master's thesis with Enzo about exoplanets and what can we learn from them, then basically I continued on and persevered and
Yeah.
also got a PhD in the same subject, and then I continued on with the postdoc, and now I'm here, and yeah, i- in this
Yeah.
uh, in this really on the verge of this new exciting adventure at
It
ESA.
is exciting.
it's also a nice path. I mean, you started from asking questions as a 5-year-old, and you're now answering those questions just putting a telescope in the sky.
Yeah.
Yeah, exactly. Putting a telescope at L2, so the Lagrangian point 2, which is a point that is stable gravitationally for anything that you put there, and you just need to give little nudges and little pushes now and then to keep the orbit, and it stays there, and you can then have the full view of the whole sky in 6 month period without having to look toward the sun. So you want to look toward outer space.
Mhm.
So that is
Yeah.
where Ariel is gonna stand. Is gonna
Yes.
sit there and look at the sky. Now you say it's a point, but just to clarify to the listeners, it's a little large. It's a point in space. It's not really a point as we intend it on the street, right? So
Yeah.
Yeah, exactly. So the point that is not a point is about
Yeah.
1.5 million kilometers away from the Earth in the opposite to the sun direction. Basically, it's not just Ariel that will be there. There are other satellites orbiting there, such as James Webb, and they are usually on so-called Lissajous orbits. So they revolve around the actual L2 point, and they keep moving, but there is a lot of space, so don't worry
Yes, so they're
about.
not gonna be hitting each other. You don't have to
Exactly.
worry, like, low Earth orbit is getting all junked up, but we don't have to worry about that with the L2 point. Not yet, anyway.
Exactly. And it's always foreseen that when a mission like that ends, there is a, a maneuver that is done to avoid that debris stays
Mm,
there
yeah.
for the future.
so Ariel, we've been mentioned this name a few times now. For whoever is not familiar with Ariel, what is it? What is the scientific mission? What is the core? What is the aim of the Ariel Space Telescope?
So let me start by this. So we are the first generation to know that there are thousands of exoplanets out there outside of our solar system. And so naturally we ask ourselves, how are they different to the planets that we know that form the paradigm of our knowledge of planets that are in the solar system? And there are so many of them. So clearly it's difficult to use the solar system as the only paradigm, and we want to understand what the solar system place in all of this is. So Ariel stands out as the first mission that's entirely dedicated to the first spectroscopic survey of hundreds of exoplanets. And in contrast to previous missions that are observer driven in the science of exoplanets like James Webb, Ariel will allow the coverage from the visible to the infrared from 500 nanometers to about 8 microns of the electromagnetic spectrum to be covered simultaneously and continuously so without gaps. And that's extremely important because you want the coverage in the visible and that in the infrared to combine the knowledge on the stellar activity, hazes, clouds that you get from the visible with the atmospheric composition that you can infer from the infrared. And you want no gap in between because it's always difficult to stitch together spectra that are taken at different wavelengths without any bridge between them and also at different times. You want to do the full spectrum at the same time in one shot. And that's what Ariel will do.
Okay. Yeah. So has it meant like really radical advancements in spectroscopy in order for this to happen? If before, it was kind of, well, we'll do this bit and then we'll do that bit and then we'll hope that we can stitch them together.
Well, technically, there is no radical advancement in doing spectrophotometric observations on this kind of wavelength range. The technical advancement for which also Ariel was selected is the concept of an aluminum telescope. An aluminum telescope of 1 meter is something that has never been flown before, and that's
Why
really
aluminium? Is it that the mirror is aluminium or the bus of the satellite is aluminium?
no, it's all the mirrors and structures. And
Oh, so
that's meant to
everything.
not everything, but the parts that are optomechanically relevant are all in aluminum. So that's meant to offer the best stability in space, as aluminum has the property that it contracts homothetically, meaning everything contracts and expands in the same way. So that ensures that you have extremely stable observations in the environment of L2, which is already very stable thermally.
And you need this extreme stability because the signals that you're looking for with the spectroscopy are really tiny. Is that why the extreme stability is needed?
Yes, so we we need to have stability in the order of 10 to 100 parts per million, depending on the brightness of the star, on timescales of an observation, which is typically lasting 8 to 10 hours for a transit. So, transit means the planet is passing in front of the star, and we are measuring the dip in the flux that we collect, that we
Mm-hmm.
receive with our telescope from the star.
Mm. Yeah, that is a long time to to have to detect such tiny, tiny signals.
And how can you make sure that you have the right precision and the right stability now if the mission is going to be launched in few years?
Yeah, that's a very good question. And so first, you design the mission with an optical, and that was I was saying before, optomechanical concept that makes it stable. Then you analyze it with simulators, so combining the mechanical, optical, thermal parts all together. And this is what is the exercise of the STOP analysis. So STOP stands for structural thermal optical analysis, and then you use this to predict the performance on ground and then in flight with gravity removed and with cryogenic temperature.
So is that the sort of thing that you work on? Because the title of like telescope scientist, it just sounds so sort of broad. I mean, so what do you do in your sort of day-to-day role?
So the telescope scientist role means that I am sort of the guardian of light for Ariel, meaning
Oh, Guardian of Light. Oh, that's like a movie, isn't
Wow.
it? Oh, yeah, like that.
You need a
so
shield with, with this written on top
Yeah,
and just hang it on the wall of your office. It sounds so cool.
yeah.
and yeah, so the responsibility is to make sure that I follow each aspect of the performance of the telescope that impacts the scientific performance of the mission. So really, I am there and standing my ground to not compromise the performance of the telescope because the mission depends on it. Because
So what
yeah, go
what
ahead.
can influence the performance of the telescope that we may not think about? So, we can think about, oh, yeah, a bigger mirror means that you're more sensitive and, you have to select certain wavelength ranges depending on what you want to look at. But what might we not think about that's really important to the light sensitivity?
Yeah, so the photons that are collected through the mirror undergo reflections, and if the shape of the mirror is not perfect, is not ideal as we designed it to be, then you lose photons from, for example, small scale effects, but also the PSF, so the point spread function that forms at the detector is going to have a shape that is not like that of a diffraction pattern of an Airy diffraction pattern.
Let me
And so
let me rephrase it very fast for the listener. When you say the point spread function and PSF, that basically means what is the shape of the image of a point in the sky, how it's gonna be reflected in your actual picture.
exactly. So with Ariel, we will do observations of point sources. So we measure stars, signals, and their relative decrease when the planet transit in front of them. The image of a point source is an Airy diffraction pattern on the focal plane, and any imperfection in the optics will lead to a deformation of this pattern and an aberrated point spread function. But also you can lose photons due to the microscopic small scales defects. That means you lose throughput. So not only is the shape of the PSF aberrated, but you also have less photons to count. And if you have less photons to count, it's more difficult to be in the
Mm,
photon noise limited regime that we all aim for.
yeah. And if that PSF is like morphed and distorted, then that also impacts sensitivity.
Exactly. Ariel has a pointing instrument that is also used for science. It's called the FGS, and one of its channels, FGS2, is used to centroid on the star, so to lock on the target and keep the fine pointing during the full observation. And it's really important to keep the light in a compact region of the focal plane to have a precise centroid, because the spacecraft is connected to the FGS centroid with a loop, and so the FGS centroiding performance eventually impacts the stability of the spacecraft. And the stability of the spacecraft is really important because we are aiming for those 10 to 100 ppms on the time scale of stability on the time scale of the observation.
I know what you are talking about, and I just can't restrain myself to intervene. So when you say tens to 100 ppm, that means that we are aiming to achieve a precision of 10 or 100 parts per million of the stellar light. ppm is part per million, meaning that 10 on 100 part every million photons is what we're actually looking at, right? And it's also referring what you were mentioning before about the photon noise limits that you were saying before, which means that this is the best we can do is just counting photons and having that as a limit for the noise that we have. And what you are doing is protecting us and making sure that we are achieving that goal of being limited only from photons.
Exactly, because there are many other things that can start creeping in. If you are not photon noise limited, you can be limited by the readout chain, so readout noise, or you can be limited by, I don't know, but it's not the case of Ariel in any way, shape, or form with dark current, for example, or with other effects.
So remind us what dark current is.
Okay, so dark current is the current that is generated in the detector due to just the fact that the temperature is non-zero, and so that induces a charge in the detector that can be revealed by your detector.
And so then I guess Ariel's cooled.
There is a cooling system that allows Ariel to reach the operating temperature of about 50 degrees. But usually, this is not the consumable that determines the lifespan of the mission, which is more likely determined to the availability of the propellant for the
Okay, to like
maneuvers.
keep it
That
at altitude.
exactly, yes. So and that the availability also depends on the injection maneuver on the L2 orbit. For example, with James Webb, they were really successful in minimizing the amount of fuel that was expended in this orbit injection, and that's why James Webb is projected to last for about 25 years. So that's a
Oh,
lot.
has it gone up to 25 years now?
Exactly. Yes.
Wow.
So that's pretty amazing that what they've
Mhm.
achieved with James Webb, and yeah, we we aim to do the same,
Hope for something similar. Yeah.
something similar. But yeah, Ariel is scheduled to have a nominal mission of 4 years plus an extended mission of another 2 years. But
Mm,
of course, these
we hope for
things
more.
can last in space, so better to inject the orbit properly and then cross our fingers
Yeah.
to use it
So
to the end.
in in your role, you want to kind of get down to the lowest sensitivity possible. And of course, you could do that if, for example, money and weight were no objects, right? I guess those two kind of limit what you can do. Are there any other kind of limitations that mean you have to balance the level of sensitivity that Ariel can get to?
Yeah, so of course we stick to the requirements that were set for the mission early on and for the flight conditions, and those are untouchable for me. And what is really the other, what I would say is not a limiting factor, but it's certainly a term to consider. Is maybe something that you don't usually think about, which is communication between people that come from an engineering background and from a scientific background, and usually they do not tend to speak the same language. So
Okay.
the role of telescope scientists is also allow them to exchange and translate and make sure
Okay.
that there is
Yeah.
no loss in translation.
So there's
Both
very much a human side to your role as well.
that's right. So Ariel is like any other space mission or huge scientific effort is beyond the hardware. Is really the people that make or break the mission. And so Ariel is more than anything a community of people, hundreds of them that strive together to elevate the knowledge of exoplanets to new heights. Because
Yeah.
with James Webb, we've had the first view, I would say, of exoplanets at scale,
Mm.
meaning tens, and eventually maybe 100 will be observed spectroscopically with James
Mm.
Webb. Ariel is a different beast in the sense that it aims for statistical completeness
Yeah.
as much as
And why
possible.
is that so important to have this large sample of exoplanet atmospheres analyzed?
Yeah, so that's really fundamental because by sampling the whole parameter space of exoplanets, we can eventually find if there are trends in the population in the parameter space, because parameter space is huge. If you think about stars in the Hertzsprung-Russell diagram, there are relatively few parameters that you are able to track that tell you the full story, that tell you how the star moves from the pre-main sequence phase to the main sequence phase and then off to the late. But for exoplanets, it's going to be much more difficult to have such kind of simple diagram to interpret because of their gigantic diversity.
Yeah. And so that's why you need the big sample is to properly probe the diversity of the exoplanets and then try and understand them as a whole. So it's kind of covering all the bases that you possibly can.
Yeah, so in the solar system, for example, we um, we are missing two classes of exoplanets that are the vast majority out there. which are super-Earths and sub-Neptunes. And it only by looking at exoplanets we found out about them. These exoplanets are in between the size of the Earth and the size of Neptune, and can be dominated by the rocky part, such as super-Earths, or by their gases, such as sub-Neptunes.
So the target list for Ariel, what is that dictated by? Is that orbital periods, or like the type of star, or the type of planet? Because I guess because this is an analysis mission, will you go with an existing list of planets that you know you want to look at, or will it also find new planets?
So this is not a exoplanet discovery mission; is an exoplanet characterization mission, and we will go there and have a target list that's going to be endorsed by the Ariel science team. Of course, it will be it will contain inputs from the Ariel mission consortium, but also the community. Then the Ariel science team will endorse the final target list that will be observed. In case there are new discoveries, the target list can always be updated, so we ensure that we do not miss on any knowledge that could be at our
Yeah.
easy to grasp with Ariel, of course. But yes, we will have a plan, and we
Yeah.
will stick to the plan
Yeah. Unless
because,
something really exciting comes up.
yeah, you never know. But basically, we will have a plan for the 4 years of nominal mission, and we will know it before launching.
So, before launching, so when we launched the mission, you mentioned that there is a huge human effort behind it. It's a human component is very important for a mission like Ariel. So before launching, you know what you're gonna do for the next 4 years. But after the launch, where is gonna be the moment when you can finally start breathing again and say, okay, the mission is working?
Huh.
That's a good one.
I know there is some panic when the rocket fuels and you just see fire under your
Yeah.
telescope.
Be like, oh no, my baby's on board that.
Yeah, you don't want to see that. And that's why the engineers have spent so much effort in building the rocket that is going to fly with Ariel inside, which will be an Ariane 6 rocket, and it will launch from Kourou, and hopefully we cross our fingers, and the launch will be smooth, and then it will move on to reach its observation location at L2, and then we will start the commissioning. So we'll see that we'll do all the functional tests, making sure that all the telecommands and things like this are working. And after that, we can do the commissioning of the instruments.
So there, is that the time that you breathe? When you get that first light?
Exactly. So the first light is really the moment that we're all waiting for, to see that we obtain the PSF in the photometric channels and the line spectrum function in the spectrometers, as we have predicted with our simulators that we've built over the years. And so that would be the defining moment. And after that, we will move on to observe.
If I need to train to hold my breath, how long should I wait?
Yeah.
Well, commissioning phase is so there is the commissioning phase, and then there is the science demonstration phase. Nominally, this should last. These are scheduled to last 6 months total before then the nominal mission can start, which lasts for another 3.5 years. So we will
So maybe we shouldn't
we
actually
will
hold our
know.
breath then.
No, you will know early on.
Long, long days ahead of us.
Yeah.
Yeah, we will know in the first months.
I
Okay.
won't sleep for a month.
I'm still not going to hold my breath if it's a month.
Yeah, but these things take time, and
Yeah. Yeah, it's got to be done correctly. Absolutely. So, Andrea, before we wrap up, we have one final question for you, which is our signature question. And people either love it or they hate it. It's like the Marmite of the interview world. And our signature, it
The
is though.
Marmite of the interview mode is
It
fantastic.
is. It is the Marmite of the interview world, right? And so our final question is this. It is, as always, If you had to choose one celestial body that represents you or represents your work, what would it be?
Yeah, so it's a hard question, and I appreciate
Mhm.
that you're trying to see how each guest responds to it, and I think it's only fair. So I will give you my preferred choice, and that is WASP 39b, and I
Yeah.
explain the reason behind. So WASP 39b is a hot Saturn, and the meaning it is exceptionally puffy.
Mhm.
So the mass is similar to Saturn, but thanks to its high irradiation that it receives from the star, the atmosphere layers are really expanded, and so it's an exceptionally high signal to noise target to look at,
Mm.
and it was used because of this property by James Webb during, I think I'm saying correctly, but the first months, perhaps during commissioning, but I'm not sure. They took the observations of WEST 39b with all of its instruments. And if you look at the spectrum of this planet, observed with James Webb with the NIRSPEC prism, you can really, really see from the spectral shape the signatures of the molecules that we've been modeling for so many years, and you see
Mm.
them directly from the data because you see this giant mountain
Just
of
there
CO2.
screaming at you.
Exactly, and it's amazing. And we've discovered that there is SO2, so a molecule that is the product of photochemistry happening in the atmosphere. A bit like the ozone uh, in Earth's atmosphere, but in a very different range of temperatures.
I love that.
And these spectra are basically the calibration spectra of James Webb,
Mhm.
because you observe the same star and the same planet with all of its different instruments, and you can cross check, and that's amazing to see, because here it's again the combination of science and of technology, and that's really what makes this my target of choice.
It's a very good
Really, really
answer.
nice. Really, really nice. Andrea, thank you. Thank you for taking us behind the scenes of Ariel and showing us what it takes to prepare a mission that will transform the exoplanet science.
I'm happy to have been here, and thanks, Jenny, and
Good.
thanks, Lorenzo, for inviting me.
Well, thank you for coming on. It's been a really wonderful episode. And we also want to thank everyone listening. Join us next time on Growing Worlds as we explore another corner of the universe and the people building the tools to understand it.